This lecture is on the various elements that language designers think about when they're creating a new language. And we're just going to go over some of the common ingredients that they think about and may incorporate into different programming languages that they're creating. Some languages have all of these in consideration and some have fewer. There is no one size fits all with any of this, so we're just going to go through a bunch of different vocabulary and concepts and, an overview of everything. So the concepts in this slide deck are just a collection of different words, different concepts, things that will be revisited again this semester. So after going through the slide deck, it should not be a matter of feeling like an expert in any of these, but hopefully it serves as an introduction to some of the stuff we'll dive deeper into for the subsequent weeks of this semester. So just keep that in mind. The way this is designed is to make sure that you get a preview of what's to come. It is not meant to be the only material for learning these concepts. As a recap and putting this into context with the rest of the class so far, let's touch upon a few things. So first of all, up until now, you've been exposed to the fact that there are different programming languages in existence. You've been exposed to the idea that programming languages represent the algorithm or like the solution for things. There's a lot of different languages out there. Different events in history have motivated the creation of certain languages, and these languages can be grouped roughly into a loose classification known as paradigms, and they act as different families of programming languages. There's different levels of languages. There's the machine level, the low level, and then there's the high level, which is meant to be easier for a human to comprehend and work with. And now, for the rest of the semester, we're going to focus a little bit more on the high-level programming languages. So in order to be able to talk about the design of the languages, we do have to go through some of the features that these languages have, or what I like to say ingredients, because it gives you a better sense of like you are taking different items and putting them together in different ways, and that can lead to different results depending on what combination you use and how you use it and so on. So the rest of this slide deck is just kind of going through, what possible options are available out there. Before diving into exactly all those ingredients, I do want to take a moment to just say that when programming language designers think about their ideas and decide what they want, they end up documenting what they have created, and formally it's known as a specification. So every programming language out there should have a specifications document, especially if it's a mainstream language such as Java that's used for 11.15 and 31.15 and 31.30, C, C++. All these different languages that you have been exposed to so far all have specifications. Python, JavaScript, they all have their own. And this specifications document should be treated like a legal document. So it's a reference manual for the programming language, and it describes every single feature of that language. And so some of the items that are described are similar to some of the concepts that will be described in this lecture. So far we've covered grammars, we've covered parsing by the compiler and how the compiler knows if the language is valid or not. And for the design of that compiler to be transferred, that knowledge transferred to the programmer who is writing the source code, you need some sort of way to communicate that. And what a lot of programming languages have evolved over time to use is in writing, because back then, we didn't have, what we're talking about, like programming languages coming from like the 50s, the 60s, the 70s, and so on. If you remember in history class, possibly, the invention of the internet happened much later, than a lot of these programming languages. The internet was not widely used in people's homes until maybe the turn of the century. And I mean, like 2000 and forward with the dot-com era. So prior to that, a lot of the documented information was on paper, so there is quite a bit of emphasis in our computer science community to have specifications written down in writing. And there are certain notations, we've covered this, there are certain notations that help with describing these concepts in a very concise way. Because, paper is expensive, printing it is not cheap. So, of course, our field in just optimizing everything will have come up with systems for notating things as well. So that's, to give you an indication of not only are the ideas written down, the ideas are written down in a certain notation. So when programming language designers are designing and they're writing down their ideas and just writing down the final version of their ideas, whatever they decided, what I'm trying to indicate is that there's different phases that they go through. They will think through their ideas, and possibly even you've tried in your exercise of working with Lex and Yak to create your own mini language. You've thought through various different options that you could consider for the syntax that you're reading in, how data should be represented, right? You've gone through this process of just thinking, like, I don't know what the best idea is, but here's where I've seen some example of doing this, so let me try to mimic that. Possibly, like, that might have been your workflow. There's no single right way to go about this. There's a lot of uniqueness to the process of designing. But basically what I'm trying to get at is that design does not happen in a single step. It happens in multiple steps. So there's often a process of analyzing to find out what is the good decision to make. Sometimes you need to find more information to make an informed decision. Sometimes you need to just try it, like when you're drafting an essay and then you edit it, as you think on the ideas a little bit more, it becomes a little bit more clear what feels right and what doesn't. The other thing that I want to point out is that there's no standard across the industry. There's certain organizations such as IEEE who may have guidance on here's what we want to see, like a rubric or a checklist to say here's what I want to see and here's the objective of describing this particular section. But beyond that, there's no standard. It's not like the medical industry who may have a lot more in the way of certification and other rules. Certainly programming languages are not all under federal regulation for how it should be created. But I don't want to say that there's nothing at all. I mean, if you're talking about a research group in a government agency somewhere, possibly they've got some sort of rule to abide by. But if you were to just create a hobby language, there's no requirement of how to document it. But, it's definitely good to take the good ideas from what's present out there. And speaking of that, it is really difficult to write good reference manuals and good tutorials without having the critical details in there. on one hand, when you have a lot of details, it helps the reader learn the thing that you've created. But on the other hand, there's also a trade off too of like if it's too much information, it's easy to lose your reader. So there's also a lot of gray area there as well of how much detail to write, how to structure and organize all your thoughts, in your specifications. And so it would probably be helpful for the overall industry to have a common standard practice, but that's going to come through the evolution of the field as a whole. And so just going through the process of designing, right? Just one more time, I just want to emphasize that design and analysis go hand in hand. When a programming language is created initially, it'll go through process of refinement, and that refinement process requires evaluating, deciding what's good, what's bad, what needs improvement, what to leave alone, right? Analyzing how it's used, analyzing a bunch of different things, evaluating, and then revising. And so, it's just like proofreading your essays when you're writing it. You want to think through the structure. Does it help the reader understand the point you're trying to mention? Are you meeting the page requirement length, page length requirement? Are you meeting whatever other like font size, margin spacing, all these other requirements? Are you hitting, like for instance, if you're writing advertising copy, are you hitting certain buzzwords in the writing? Are you writing at the level of the reading level of that's appropriate for the reader, right? Because if you were to write for children versus your peers versus a scientific community focused in a niche area, there's just going to be different words used, different structure, and so on. So it's not a one size fit all. That's the point I'm trying to make here. It's also going to be good if I once again bring up, like, there is a long history of a lot of different programming languages that have been created over time. So this chart starts at 1954 with Fortran, and so it's kind of just focused only on the high-level programming languages. So it doesn't say anything about the assembly languages or the machine code. Okay, this is a chart that focuses more on 1954 and forward in time up to 2001. So there's been a few new languages since 2001 that are not documented here. This image was created by this group here in the footnotes down there. So I did not create this, but I just thought it's a nice visual to give you a sense of, like, it's not just me talking about a lot of different programming languages. There is a whole world out there of people who talk about the different languages, who care about how the ideas from one language may have influenced the creation of another one, or maybe not so much the creation, but maybe somebody, like, for instance, decided that one language didn't have enough features, they're just going to create the next one, and they're just on an alphabetical naming scheme, so they went from B to C. Others are just, they have an entirely different idea. So for instance, Lisp-like languages are going to be very different from the ones that we've seen with the curly braces around here. And then we've got these other languages with a totally different structure. And then even like more recently, you have something like Rust that's going to have borrowed ideas from a lot of different languages. So this is to show there's different paradigms, there's different ideas happening. Some of these describe, the connection between different languages. This chart also shows the color code, so it's got the different, like, active versus protected versus endangered and so on. So if you just want to take a few minutes to look through, that could be like a really interesting thing. And I'll just give you random trivia facts that you can mention in future conversations with other programmers. All right, so now we've gone through a lot of contextual information. So now we can dive into the ingredients. Another way you could call this is maybe anatomy, but I think I like the word ingredients a little bit more than anatomy. So here they all are on the screen. The one note I want to make about this is that this list is depending on the author of the book or paper or talk that you are consuming. It could be slightly more, slightly less, but generally these are like the main things. It's like, for instance, if you were to talk about, and if you're cooking, right, you've got salt. You could say there's sea salt, Himalayan pink salt, regular table salt, kosher salt. Like these are all the same, like for flavoring a salty flavor, but there's slight nuances if you want to go into like that level of detail. So that's what I mean about it. Depending on the author, this list could be slightly different in how it's categorized, a little bit different in the exact words used, but roughly, it's going to be this. So when I went through all the papers and books that I was reading through to come up with this final list, the way I decided on this was just what made sense, like common sense for me, and then also what seemed to be prevalent across all the things that I read. So that's how I made my decision for saying, like, here's all the things that, the ingredients that exist when programming languages are looking for different languages, looking at different ingredients, when programming language designers are using different ingredients to create their language. The way that I'm trying to define, or I should say describe and lay out these ingredients is if, say, for instance, we have a table structure like a spreadsheet, and we had for each row the different language or the paradigm involved, right? So it's going to just be ingredients that are common across all these different languages, all these different paradigms. So the way that I see it in my mind and I visualize this is that the different ingredients, there's so many of them, and then I'm just laying them out like this. So just I'm going to go through them one by one. And the way in my mind that it works is it's just these rough sort of like dimensions to consider. And then from there, within each of the constructs, there's going to be specific elements within each of these constructs. So this is kind of like the simplified one level view. This is sort of like the more nuanced, way that I'm thinking about it in my head as I present all the rest of the slides in this slide deck. So the first one, variables, names, bindings, etc., is what it refers to. The word variable there, that key term, you have heard of it before. You have to declare a variable in Java before you can use it. These are all declarations. It's basically a way for the programming language to tell the machine, save some space and save this keyword, this name that I want to use, with this value stored somewhere. It's basically a way to bind the name that makes it easy for the programmer to refer to the value once again, and then for the machine to know like there is that mapping. So I thought this image of these locations pointing in different directions, I thought that was a good visual to explain what's happening under the hood, because the idea of having these declarations is to allow the program, and by program I mean computer, when it's executing the program, to be able to know where to point to various places and where to go to get the values needed. The names themselves, like every programming language will have different rules are on like, actually this is the slide, on like the length of the name, whether it allows spaces, whether it's case sensitive, and so on. So language designers would have to think through what are all the various possibilities and what do I want to limit it on? And then just how the purpose of the variable is that it's an abstraction of memory cells. So instead of saying hash whatever value of that memory, a name is much easier to remember, right? And this is kind of similar to the concept of IP addresses to domain names. What's happening there is that the domain name is mapped to an IP address, and to say a domain name with the name, it's much easier for the human brain to remember compared to a random sequence of numbers. And so that's kind of like the concept here with the variables, where using a name, like for instance, if we had a variable named pi and the value is 3.14, it's much easier to remember the word or the name pi as opposed to the value. Now, this is a very silly example where it's not that difficult. But if you had something more complicated, some formula maybe for calculating the trajectory of, I don't know, space travel, for instance, and you just want to save that formula, the value of certain constants as variables, and then maybe you could also give a name to that formula, and that just makes it much easier to remember, because then you can say it's so-and-so formula as opposed to like every single little detail. So that's the first construct, the variable names. Binding is a word that you saw on the slide a few slides ago. So this is the association itself. So binding is just a jargon, more specific word for this concept of creating an association. There is binding that is static, and then there's binding that's dynamic. And so depending on the language, you'll see that sometimes you've got the variables, like once you've declared the type and the name, you can't change it ever again, or the value also. Other languages are a little bit more flexible. And so depending on how much flexibility you want to give your programmers, this is another area to think about. Some more terminology. You might see the word visibility, which goes to the concept of whether you can see a name or not. There's reserved keywords. I think you've seen this before in programming languages. It just means these are words that you should not use as names for new variables. Then you also want to think about the scoping. So for instance, where is that value, that variable allowed to be used? The name, is it local, is it global, and so on. Next concept is data types. This is talking about the way a certain value could be used in a program. So the reason why I have this picture of the geological substrates is because it gives you an idea of, values are all values, but then there's different types of values. So for instance, if you have a Boolean value, you could use that for conditional, checking for conditional, but if you have like a number or a string, it's a little bit harder to check if it's true or false because it's not a Boolean. And then also if it's, for instance, a number, you don't want to try and use it as a string. You could probably imagine certain use cases where it's not very useful. Or if, say, for instance, you've got a string and you're trying to do arithmetic on it, you would then, in a lot of languages, have to convert it first, but some languages are smart enough to do the conversion for you, and then they could still do the arithmetic. So data type, it definitely does matter. Also, some languages may use the data type as a way to allocate memory on the computer. And so it definitely helps to think through the way that the organization scheme of different values. Here's an example from Java. So this may seem familiar to you. You've got primitive data types, such as Boolean, character, numeric, integer, with the different kinds of integers, with different space requirements, and then floating point with float or double. And I think you've seen charts before that may say, like, here's how many bytes allowed, or here's the length of the type allowed. And for certain functions, you could only pass this kind of value, not that kind of value. And then the non-primitive data types include strings, arrays, and then other data structures. So all of this, what I'm trying to show is that every language has some sort of hierarchy when it comes to data types. Some are a little bit more layers, some of them are less layers. It just varies. Here's another example using C++. You can have primitive types first, so very similar, integer, character, float, double, and so on. You would have derived types, and then you can have user-defined types. And then there's different rules for each of those. So it just becomes, when you're working with the programming language, like if you're learning a new language, you're just learning the rules that the programming language designer has laid out for you to work within. So there's some general concepts or like questions relating to working with data types. Some of the things that a programming language designer might think about is, how many do I want? How fine-grained of data types do I want to have the programmer represent? What are the rules for all of them? Are they static? Are they dynamic? Are they strong? Are they weak? Etc. Are they parameterized? Are there dependent types? What's the hierarchy? How do I organize collections? And so on. So lots of things are thought about with that. Type checking is also important when it comes to data types. And this is the activity of ensuring that the types of operands of an operator are legal or equivalent to legal type. So you might do type checking of, say, for instance, you're only doing arithmetic on numbers only, right? Or maybe like Java, where you don't want to mix the arithmetic of an integer and a floating point number. You just want a single type only. These are all possible reasons for type checking. Next concept, expressions and assignment statements. Okay, so I thought this image might be a good example to show the abstract nature, the patterns that you're creating when you write an expression. So it's basically saying we can have the different types of values in a certain statement, and sometimes these evaluate to a single value, sometimes it's just only writing that expression out. So the expression is really to define a computation of values. It's usually built from operands and separated by operators, and this expression is fundamental to expressing logic in a programming language. When it comes to expressions and working with them, you want to think through, is there a precedence to the operators? Does the parsing algorithm care about the precedence of operators, the associativity, and so on, the evaluation order, side effects, eager versus lazy evaluation, and so on. Here are some examples from different languages, and this is coming from the textbook Programming Language Pragmatics, Chapter 1. It's one of the images from the book, so if you flip through that, there's a PDF in the Programming Language book folder. That's where I got it from. So, for instance, if we have this math formula for calculating the greatest common divisor between two input numbers, you know what it is in math, but then every programming language will have its own way to express the logic. So this is just to show the different ways a programming language designer can come about making their decision of how they want to express the expressions. Other concepts relating to expressions is just, what's a constant, deciding what's a constant, what's a variable, deciding on symbols such as parentheses, arrows, function calls or operators, what are the special symbols and what are reserved, what are not, what are the symbols to denote an assignment statement, and all of that. So lots of things are thought about here. This is where semantics are a little bit more important for the programming language designer to think about. The next concept here is control structures. So control structures is a fancy way to say functions or flow of logic. The reason why I have this picture of a freeway, like expressway, intersection point is to show the idea that programming, like source code, a program source code has a flow of logic for data to flow in a certain direction. And depending on certain keywords such as if, switch, case, loops, and so on, it directs the flow of data either to loop over itself or to separate directions and so on, right? So it's kind of like when you're driving and you're following a GPS and it says make a turn or stay on whichever lane, because that lane's going to take you in a certain direction. So, that's programming. It's like plumbing. It's how data flows. And so control structures is to say, how does the flow get shifted? And, how do you define that flow of data? There's a couple more specific keywords relating to, or terminology relating to control flow. So they are listed there. And this shows some examples of how the flow of data can work. So the first one on the left here is just like a simple decision flow. You can have option 1 or option 2. It could also be depicted like this, where you've got selection. Actually, these are both selection, the two on the left. And then in the middle here, we have iteration, which refers to if you have a loop, you can iterate through. And then we have procedural abstraction. So these are common abstraction patterns since the 1960s. So the programming languages since the 60s have all these patterns for their programming languages. These languages allow the programmers to have logic that flow in this kind of way. So procedural abstraction is just saying I can create a function and I can repeat using that function. It's bound to a name, and I could just call that instead of trying to rewrite the same logic. And so that leads to another concept here. So not just the flow, but now this idea of procedural abstraction is this concept of subprogram or subroutines. So you'll probably have heard of, especially the older generation, use the word subroutine. It just means function or method. Depending on whichever language you're working with, it's either going to be a function or a method or a subroutine or a subprogram. It's basically talking about process abstraction. So it's saying instead of rewriting the same few lines of code, I'm going to call this other name. So I just thought maybe this, train carrying stuff, following a certain schedule, I just thought maybe that is like a nice sort of way to talk about the abstract nature of the subroutines, because you could say, if I want to go to so-and-so location, I'm just going to go on this train that's running at this time, and it's going to take me, the track is laid out, it's just going to take me to where I need to go, and then somebody else is going to drive, so that's the idea of a subroutine, where it helps with the ability to, for the programmer, it helps with holding all the ideas in your mind, because you're not worried about handling a million lines of code all at once. You've got different areas to just, collapse the code, so to speak, and then make it easier to reason with. So let's see. I mentioned that you can associate a name with the procedural abstraction. So, that's basically the technique behind writing a function. So the fancy words is to say a programmer can bind a name to the procedural abstraction. And that procedural abstraction is the subroutine. Most subroutines are parameterized, and this is a fancy word to say it takes argument parameters. It takes input. So, you could define how many inputs, or like a programmer of a programming language can define how many inputs, but you as a programming language designer can also say, a language can limit the number of arguments, or there's like a certain default value, or no functions can take arguments at all because you want things to be expressed another way, or so on, right? So there's all these thoughts that you could have when it comes to abstraction. And there are semantic rules with that. So here's just a few: pass by value, call by sharing, pass by result, call by result, and so on. And just once again, even though I'm glossing over a lot of the concepts here, it is meant to be an overview of like some of the keywords and ideas that are thought about with each of these. So there are some design issues for subprograms. I alluded to a few of these in the earlier slide, and now here's like some questions that a language designer might think through. Do I want programs to be generic? Are they going to have local variables that are static or dynamic? Will we check the parameter types, or is that left up to the programmer? And so on. The next concept is nesting and scope. And this is basically talking about how you can organize the variables in, the variables are values. So this is to talk about how you would organize values for a program. I thought a bento box was a nice example to say you can separate out different elements, and then just when you package it, it's laid out, it's separate. Or you could do something like fried rice where everything's just all tossed in together, right? So it's just up to you how you want to choose the presentation of stuff. So the scope is saying a little bit closer to the bento model, where you've got specific areas, and then your values will make sense within that specific block, but maybe not elsewhere. And it's up to you as a language designer to say if it is restrictive or not. Some languages you've probably seen do have this concept of local scope. Others maybe do not have it. Another concept is abstract data type. And this is another form of abstraction. This is very common in object-oriented programming, where you define a class and the objects, and then you describe how state is handled and the behaviors for these different objects. So it's just a different way of abstracting. So I think in a few slides ago we were talking about how you want to write less code somehow, right, with procedural abstraction. Well, when you're working with certain types of programming problems, such as maybe working on a graphical user interface, maybe you have a certain widget on the screen that you're going to reuse a lot in a lot of places, so maybe you want to have a template for that, and then depending on which page it belongs to at that time, it'll have different state and different values. Concurrency is another concept, and it's about how the machine handles the processing of all the data. Some programs allow for concurrency, some do not. So there is a difference between concurrency and parallel multi-threaded work. So a lot of keywords relating to concurrency, and this will be revisited later. Exception handling is really important. You know, you've seen where programs may have bugs, like for instance, if you divide by 0, it may be a legal syntax, but maybe it doesn't make sense for the program. And so maybe you want the programmer to think about how they would avoid certain situations that won't have semantic meaning. Or maybe you have a restriction on the type of arithmetic that can be handled. For example, maybe you want floating point arithmetic only, so all the integers have to be converted to a floating point first before you do arithmetic. And then maybe you want to allow the programmer to be able to express that sort of things, right? So exception handling in when you design a language is to allow for these like try catch or other like error handling stuff. So you just want to find a way to allow them to express those edge cases. You could also define what kind of errors there are, and is it a type error? Is it a memory error? Is it other, like syntax or lexical errors and so on? So speaking of that, there are some hardware limitations when it comes to language design. So as much as a programming language designer can think about how awesome their language is and how well it fits the problem domain they're working on, sometimes it is limited by the programming or the computer that the programs run on, right? So here's an example of floating point errors. So what is this? If you were to try in Java or Python to do this arithmetic specifically, so 0.1 plus 0.2, you're going to get this odd number of 0.3 and then a bunch of zeros followed by 4. This is what they call a floating point error. So because of how memory is represented, on the hardware, you have the ones and zeros. So computers can only natively store integers, so they need a way to represent decimal numbers. The representation is not accurate. So if you have a base 10 system, like we do in the real world, the memory is going to be base 2, and so it just doesn't align very well. And I think this link has a nice figure that explains. Yes, so we don't have a nicely spaced out using the base 2, the conversion from base 10 to base 2. So there's rounding errors that happen. Okay, so back to the slides. So rounding errors happen when the number can't be stored in the IEEE floating point representation that's used in an expression. So when it's where each bit is doubled, so decimal numbers are stored where each bit is doubled. So it's easy to represent 1 over 2, 1 over 4, 1 over 8, and so on. But when you have like 0.1 and 0.2, it's not so easy to represent that. And so here's a bunch of other links to read more about it. And then let's see, next thing. So there are some standards by IEEE about the representation, about the rounding errors that happen. So it's just another thing to consider, like when you're programming, as awesome of a job as you do just want to consider like where your program might be implemented on and how that might lead to possible issues. So if you wanted to learn more about, specification of hardware, IEEE standards 1003.1 to 12, the POSIX group, is a nice way to get a sense of operating system standards. Okay, so what's next for our class? We're going to cover some of the constructs more in full. So we'll just go through different paradigms, just look at how the design trade-offs, how they look like.